This presentation is going to be on information gain and entropy, or entropy in information and data. So at the very highest level, entropy is defined as the unpredictability of a data set. Here is a more detailed definition of entropy. First, information entropy is a calculation in information theory associated with a random variable, and it's thought of as the level of information or a surprise or the uncertainty inherent in a variable's possible outcome. Entropy is the expected value of the self-information, so that's the value of the surprise. Entropy also quantifies how informative or surprising the entire random variable is. Here we see the inverse relationship between the probability of an event versus information. If the probability for an event is very low, say right here, when it occurs, the information content is very high. Here is the formula for calculating entropy, and it is this right here. E entropy equals negative C summation over I for the probability of I log 2 probability of I. So C is the number of classes, Pi is the probability of randomly picking an element of a class, and that's the proportion of the data set made up of class I. Let's show an example here with fruit. We will have 1 banana, 2 apples, and 3 oranges. So that's 6 pieces of fruit. And going back to our entropy formula, we have E equals negative probability of banana times log base 2 probability of banana plus probability of apple log 2 probability of apple plus, and it's right here at the end, probability of orange times log base 2 probability of orange. Let's apply our formula then to these 6 pieces of fruit. We know that the probability of bananas is 1/6 because 1/6 of the data set is bananas. Similarly, the probability of apples is 2/6, and the probability of oranges is 3/6. So when we apply the entropy formula, we have it right here. E equals minus 1/6 log 2 times 1/6 plus 2/6 log 2 times 2/6 plus 3/6 log 2 3/6. If you calculate that out, the answer is 1.46. What would it look like if we had a data set of all 1 fruit? So let's consider 3 oranges, and that's our entire set of fruit. Okay, what would the entropy be? Well, E equals negative 3 over 3, that's 1, log base 2, 3 over 3, that's 1. If you calculate it, it's 0, which makes a lot of sense because there's perfect information, there are no unknowns, and so we get an entropy of 0. What then does 0 entropy mean? To reiterate, 0 entropy means perfect knowledge. It also means there's no new information. From now till the end of the video, this is the table of fruit that we're going to work with. So this table of individual fruits, it has colors, weight in grams, and calories. So here are the fruit, and we see that we have bananas, apples, and oranges. And we have a column of weight in grams and calories. So the question that we're going to ask is, what is the entropy of this data set? And it's important for us to know that in this data set we have 6 bananas, 6 apples, and 6 oranges. The entropy calculation is right here for this 18 pieces of fruit data set that we have. And given that there's the exact same number of bananas, apples, and oranges, the calculation appears to be pretty easy. It's 1/3 log base 2 1/3 plus 1/3 times log base 2 of 1/3, and again right here. So it's a very high level of entropy, which is 1.584. So we're going to call that entropy before we did any split, which means that there's a high level of entropy right now. And if we do a split of the data based on a characteristic, we're going to see if we can lower that level of entropy and have information gain. Here is an XY chart that shows the number of calories for each piece of fruit here on the x-axis and the weight in grams of that same piece of fruit on the y-axis over here. Notice that we can't tell exactly which piece of fruit because they're just data points, but we kind of know that these right here are the oranges. And we know that these are the apples and the bananas just because I know their caloric content. So that's going to be important for us when we look to make a split. The question is, can we reduce the entropy by creating a split in the data? What if we split the data and created two groups? Group 1 will be this left branch, and that's going to be those that are under 80 calories. And group 2, this right branch, is going to be the group that is more than 80 calories. There are 6 fruits with less than 80 calories and 12 fruits with more than 80 calories. On the left branch, there are 6 oranges. And on the right branch, there are 6 bananas and 6 apples. We need to calculate the entropy for the left and the right branch. Here, the entropy for the left branch is equal to minus left paren 6 oranges over 6 fruits, so that's 6/6 log base 2 of 6/6. Well, when you make that calculation, the entropy is equal to 0. So that's 1 log base 2 of 1. That entropy is equal to 0. Here is the entropy for the right branch. So E right here, and it's equal to negative 6/12 means there's 6 bananas out of the 12 fruits, log base 2 times 6/12, plus, now we consider the apples. 6 of the 12 are on the right side are apples. 6/12 times log base 2 times 6/12. And that entropy, when you calculate it, is equal to 1. To calculate the total entropy after the split, then, we take the entropy on the left side times its weight plus the entropy on the right side times its weight. So the entropy on the left side was 0, and it doesn't really matter, but the weight was 0.333 because of the 18 fruit, 6 were on the left side, which were oranges. Now we add to that the entropy on the right side. We calculated that to be 1, and its weight was 0.667. That's because 12 of the 18 fruit were on the right side. Now we can calculate the information gain. So the entropy before the split was 1.584. The entropy after the split was 0.667. So information gain is equal to the entropy before minus the entropy after the split. So the entropy before was 1.584. The entropy after the split was 0.667. So the information gain is 0.917. Therefore, the information gain is equal to the amount of the entropy that was removed, which is 0.917. To summarize information gain, entropy characterizes the purity or the impurity of an arbitrary collection of examples. Information gain is the expected reduction in entropy caused by partitioning the examples based on a given attribute. Let's see how to calculate entropy in SQL. Here is my fruit table, which is identical to the one that we had in Excel. Here is the calculation for entropy. The first thing that I do is I make a common table expression right here to give me the number of each fruit. So there's my select fruit and give me the count. So that'll say that there are 6 bananas, 6 apples, and 6 oranges. This CTE gives me the percentage of each fruit. So 6 of the 18 are apples, 6 of the 18 are oranges, 6 of the 18 are bananas. So it gives me the, in this case, the probability, which is 1/3. Once I know those two, I can go do my calculation, which you can see has the log functions here, to give me the entropy of this table on fruit. This is what the results will look like. And we see fruit, total entropy, and it is the maximum possible entropy because there's an exact split of apples, oranges, and bananas. Here is that same code in SQL Server. So I'm going to highlight my 2 CTEs and then my formula to calculate entropy. I will execute that. I'll scroll the answer, and we see that it's the same answer that we saw on the slide, and that's the total entropies right here. It's really close to the maximum possible entropy, and the percentage max possible entropy is just right there to 100%. So in conclusion here, I have built 3 stored procedures that are going to help me calculate information gain. So here's the first one, and it's the entropy stored procedure before the split. So we've seen that logic in the previous slide, and now it's in a stored procedure format that you can see. And it's going to calculate the total entropy without the split. This is tiny writing here. We'll see this in SQL Server in a moment, but this is a stored procedure, and it's only the first half of it that calculates entropy for the left branch and the right branch, so it's for the split. And again, we did that based on the 80 calories. So you see right here in this common table expression, the left branch says where calories are less than or equal to 80, and here in the right branch it says where calories is greater than 80. Here's the second part. It's in the same stored procedure, and it calculates all the way here, calculating the entropy, and then we put that value, that split entropy value, into a table. And so we select that into T entropy 1. When we get to the information gain stored procedure, we look at the other 2 stored procedures, the total entropy and the one with split entropy. We calculate the information gain right here, that is the entropy before split minus the entropy after split, and then it's returned. Let's look at this now in SQL Server. Just to reiterate, here's the fruits table with our 18 fruits that we're working off of. And so we're querying that. Here is the stored procedure for the total entropy, And we come down to our calculations here, and right here is where we do our log formulas to calculate that, and then we can run the stored procedure with an exec statement. Here's the split entropy. It's really long because you have to calculate the entropy for the left branch and then calculate the entropy for the right branch and give those proper weighting and then return those as a single number. So we have a left branch, and then here we start with the probability on the right side where the calories are greater than 80. We count the number of fruit here, then we have to calculate the number of each of the 2 fruit and get our probabilities with our log function. And here's some of our final calculation. And maybe I can scoot this over so you can see the whole thing. And so we make this CTE right here, that's the grand calculation. Then I take the split entropy from this CTE and insert it into a table. So this table right here is going to hold just one value, and that's going to be the split entropy. And here is the execute our stored procedure. Finally, here is our information gain stored procedure that you can see the name right here. In that, we have to drop the 2 tables that are being returned here. We need to drop those so that we can run the stored procedures and build those again. Then we declare variables here that are going to hold the 2 entropy values, the one before the split, the one after. So I execute the first stored procedure here. I execute the second stored procedure here. I grab the before entropy here and put it into result value. And here I get the at result 1, that's the entropy after the split. Then I make my variable at information gain is just equal to the before split entropy and then the after split entropy. And then I display it. So let's execute the stored procedure, scroll up, and you'll see it made that calculation right here that we saw earlier. So that's running those 3 stored procedures in SQL Server. So to conclude, the calculation of entropy and information gain is the first steps in doing decision trees. We have to understand those concepts as we get into building decision trees. At the end game with a decision tree is to find the best split. And the best split is the one that gives us the maximum information gain.